Hello, this is Math with Beth, and we are going to look at applications of exponential decay. If you have not already seen my video on uninhibited growth, you might want to watch that first because I'm not going to repeat some of the stuff I did on that. I'm going to assume you already understand it. So if you already understand exponential growth typically would start here and be going up. So this is just the opposite. Because of this negative, it has flipped the graph and now it is going down. So this is some kind of case where something starts high and gets lower and lower and lower and lower until it gets close to zero. So one example is this. If we have something like strontium 90, which has a continuous decay rate of 2.8% per year, the rate of change of the amount N of this radioactive isotope is given by this. This is saying that the derivative of this equation is this number times the starting equation. So I talk in that other video that this is only going to happen when you have something with an e to some exponential power. So the first step is finding the function that would satisfy this equation. And they say let n sub o represent the amount present at t equals 0, which just means the starting amount. So they're just basically telling you, instead of p sub o, make it n sub o. Because this equation is used when you have a starting amount. E is just e, because remember it's a number, 2.71. K is the rate, and t is the time. So in this case, all you'd have to do is say the equation must have been n sub o, that's our starting amount, e, our k must have been this, because that's why the derivative had that out front because of the chain rule. That's it. That must be the equation. So B is now going to ask us to do something with that equation. They say if 1,000 grams of strontium 90 is present at t equals 0, so basically they're giving us the starting amount, so this is the n sub 0, how much will remain after 70 years? So they're also giving us the t. So we would say n of 70, this is just the explaining what we're doing. We're using the equation and plugging in 70, would be 1,000 e to the negative 0.028 times 70. So this is easy to solve because we don't have to move anything around. We can just put all of that in our calculator and we would get 140.9 if we're rounding to the nearest tenth. So that's how much would be left after 70 years. Next part is asking us to find the rate of change of the strontium 90 after 70 years. So rate of change always means derivative. And then again, they're giving us the t. So first, remember that the derivative was just this times the original equation, right? That's what they told us here. So it's this times the 1,000 e to all of this. And again, we're plugging in 70. So plug all of that into your calculator and you would get this, which means that at 70 years, this is the rate that it is going down per year. It is losing this many grams per year. And then finally, after how long will exactly half of 1,000 grams remain? Well, half of 1,000 would just be 500. So they're basically asking us how long, what would be the t when there's only 500 grams left. So this time we would plug the 500 over there because that's the present value. And then this time we have to do a little more work to solve because it's t that we're trying to solve for. So hopefully you're okay on your exponential rules, but if not, you can watch me do it. So I would first divide by this 1,000 because I want to get the e all by itself. So now I'm here. And now to get rid of the E, because I would like this to just be by itself, you take the natural log, the ln of both sides. That wipes out the E. So ln 1/2, which is just a number, but it's probably not a nice one. So I'm just going to leave it ln 1/2 for right now, equals this. And so the last step would just be to divide by the negative 0.028. So now I'm going to pick up my calculator and do all of that at once, because if I did it piece by piece, I would probably round at some point. We don't want to do that. So I'm going to do all of it at once. So I'm going to do ln 1/2. Make sure you end your parenthesis, then divide it by negative 0.028. So the answer is about 25 years if you rounded to the nearest year, because that's what we were trying to find, the time. How long would it take for there to be 500 grams left? Okay, so what we just basically did was we found the half-life, because we found the time it would take for there to be half as much left. So anytime you want to do that, you can do what we just did, or there is some shortcuts. So these are the shortcuts to find the half-life. So you can do, depending on what you have, K times T equals ln 2. So you can move things around. If you're trying to solve for the K, but you have the half-life, that's what T is, then you can do ln 2 divided by the half-life. And if you just have the K, you can find the half-life by doing ln 2 divided by K. So these are shortcuts to find the half-life. So let's try the next one using one of the shortcuts. Plutonium-239, a radioactive product of a functioning nuclear reactor, can be deadly to people exposed to it. Its decay rate is about this, which means that is our K per year. What is the half-life? Now remember, since it's decaying, this is really negative, right? The K is really negative. So to find the half-life, we would do ln 2 divided by our K, but remember this is percent, so we really need to move this decimal 2 more places to the left. So there's a bunch of zeros there. So we would really do this in the calculator to get 24,755 years. So definitely when you put it in the calculator, make sure you end the parenthesis after the 2 before you divide, or else you'll get a different answer. All right, and the last one, following the birth of their granddaughter, Jean, Sylvian, and Angela went to make an initial investment, PO, that would grow to $10,000 by the child's 20th birthday. Interest is compounded continuously at the annual rate of 4%. So this is like our K. What should the initial investment be? So we're basically talking about this type of case, but what they've really given me is the present value. They want to know if we want to end up with $10,000, what should this initial investment be? And they gave us the K, so we just need to make sure to make it a percent. And they gave us the T because they said they want this to happen by the 20th birthday. So to solve, we just need to divide both sides by E raised to all of this. So you just got to make sure you do that carefully. So again, here's me doing it in just a scientific calculator. 10,000 divided by E raised to the 0.04 times 20 in the parenthesis. There we go. So the initial investment should be about $4,493.29. Those were just a few examples on how to use the exponential decay, even though this one was really the growth, to find the answer to some of these application problems. If you need more examples than that, or you have any questions, just let me know. Thank you.